Now we're on with one person in attendance. Okay, if Mochi comes, she must make herself known. All right. So I don't know where to start now because I was going to do something for Mochi. Right. She wanted to know about something about E cell potentials, E electrode potentials. W, are you all right with that? Shall I continue? All right. Good. Okay. And what we're going to do is we're going to change concentrations. Okay. Now let's take this one. See you. Oh, Ndibo's here. Woohoo! I shouldn't really say that. I shouldn't mention names, should I? Because it's going to go on YouTube. Ndibo, how are you, dear? You've doubled the audience. All right. So let's have a look at the copper system. Okay. Now I might be wrong. The E electrode for this is plus 0.34, I think, something like that. Or is it 3.6? It's 3.6. Okay, so there you go. Let me get rid of that. It's 3.6. Yeah, we do. We are, dear. Why? We are doing a little bit of it. Yeah. Debbie, what do you want to do then? I sort of had this in my mind for Mochi, and she's not here, but I'm sure she'll come back. But is this okay? No, we are going to, but we're going to do this for like 3 minutes, 5 minutes. All right. So anyway, all right. So now, what does this mean then? Well, as you all know, I'm sure, if we connect it to, yeah, you can kick Mochi for me tomorrow. If we connect this to a hydrogen cell, which is in the gaseous state, 298K and 1 atmosphere. Okay, I'm trying to draw a very quick hydrogen cell here. Goes up there, goes across. Okay, and we're going to connect it to the copper system. There's a bit of copper. Okay, and this is my hydrogen half cell on the left. And obviously, this is the hydrogen ion concentration of 1 mole per decimeter cubed. And this, what have we got here? We've got this guy here. Okay, there's a salt bridge. And then we've got that. And this is copper metal. Sorry, no, that's not right, is it? This is copper metal. And inside the solution, we have copper ions. Okay, and this is 1 mole per decimeter cubed. Okay, are we happy with that? Are we good so far? So far, so good. Yeah, I guess. All right. So what I'm gonna do is, how about Ndibo? Could you say something, dear? So I know you haven't run off somewhere. Just type something, dear. Anything you want. Oh, was she gone as well? Tappy, at least you hang around. Right. Now, oh, well done, Dibble. All right, so this is the system. So what's going on here? Well, the electrode potential is plus 0.36 volts. That means, what does that mean? It means the copper is the positive electrons and the hydrogen is negative. That's what it means. That means electrons go from the hydrogen to the oxygen. Okay. And what equation is going on? Well, this is the copper system. Okay. Are we all good with that? Okay. And the copper has a cell potential, an electrode potential, sorry, I should say, of plus 0.36 volts. Everyone's good so far, and this is under standard conditions. Okay, so if I hook this up, I'd get a voltage of 0.36 volts. Okay, now let's have a look now what I'm going to do. I'm going to increase the copper ion concentration. I can't do anything with the metal. The only thing I can increase or decrease is the copper ion, the copper solution concentration. So I'm going to increase this. Now we're going to use a couple of ways. We're going to use the way I kind of remember it. We're going to use Le Chatelier. Okay, this is my first method. All right, so if I'm going to increase the copper ions, which way will this equilibria proceed? Will it go to the right or to the left? Yeah, well done. It's going to go to the right, so it's going to go to the right. In other words, copper ions here are going to go onto the piece of metal, and they're going to make, because the copper ions are positive, the copper is going to become more positive. Does that make sense? This thing here, this bit of metal, gets more positive. Yeah? Hold on, so in the case with electric potential going to become a yes, dear. Yes. All right. So it's going to go over there. So it may have been at 1 molar, 1 mole per decimeter cubed, it was plus 0.36 volts. But let's say at 2 molar, now I'm guessing these numbers, obviously. It might go up to 0.4. It becomes more positive, okay? For the reason I've just said, it becomes more positive because as these go over there, okay, they suck out electrons, okay? In other words, more copper ions go onto the electrode and the electrode becomes more positive. So it might increase like this. Okay, now this is E. E standard electrode is 0.36 volts. The E electrode is equal to 0.40 volts. Now, what am I going on about here? Well, the first one is under standard conditions, and it has the standard sign, but the second one is not standard conditions. And so we don't put the standard sign on the second one. Does that make sense? So if I increase the concentration of the solution, the electrode, listen to my words, the electrode potential increases. Will ever be asked to predict the new electrode potential? Yes, dear, we can. Okay, but I'll get to that in a minute. All right. So are we understanding so far with what I've done so far? Excellent. All right. So we understand so far what's going on. I increase the concentration. Now, for fun, because we've got to make sure everything's cool, we're going to decrease. That doesn't look good, does it? We're going to decrease the copper 2 concentration. Now, if I decrease this, more copper atoms will form copper ions, and doing that, more electrons will be produced on my piece of metal here. So if I decrease the concentration, the electrode, the actual bit of metal, would go negative. It would go to, it would become more negative. That's right. So, and I'm going to guess, I don't know. So if I say 0.5 moles per decimeter cubed, I'm going to say maybe it's going to go to 0.3 volts. Is that clear? Yeah? So we have E electrode here, and I'm going to say 0.3 volts, and this is 0.5 moles per decimeter cubed. Okay, now this is always the case. If I increase the concentration, the electrode potential will become more positive, and if I decrease the concentration, the electrode potential will become more negative. And this is a way of looking at it. Okay, another way that there's absolutely nothing wrong with what I've done, but I'm going to look at it again. All right, let's have a look at this. Copper 2 plus 2 electrons gives, Isha is here. Hello, Isha. All right, so if I do Cu2 plus 2 electrons gives Cu, this is going to be plus 0. My pen stopped working. Why have you stopped working? Oh, there it goes. All right, go back. This is going to be 0.36 volts. And now if you just look at that equation, all right, without worrying too much, if I increase the copper ions, if I increase these, it's going to go more right because of Le Chatelier. And if it goes more right, it's going to become more positive. If I decrease the copper concentration, it's going to go that way, and it's going to become more negative. Now, these are electrode potentials. Okay, I think everyone's good so far. We all get that, do we? I hope. Now, is there a way? Oopsie daisy, that's gone wrong. Is there a way to calculate this without me just guessing these numbers? And there is. Anyone know what I'm going to talk about now? How do we put numbers on this? How is this calculated? Yes, the Nernst equation. Okay, now this is a big deal. All right, the Nernst equation, what it does is it calculates electrode potentials. How do you spell potential? Potentials. What it doesn't calculate is cell potentials. Okay, so it doesn't calculate cell potentials, it calculates electrode potentials. And now you're thinking, what the hell's that? Well, if I look at the copper system that we've done already, now you might have to help me here because I honestly can't remember the Nernst equation. I'm going to guess it, I think. This is the E electrode is equal to E standard electrode. Oh, I can't do this anymore, guys. I have to go to the syllabus and get the equation. I just can't remember it. I know it roughly, but it's not good enough, is it really? Now, don't worry, I haven't left you. I know it's 0.059 and oxidized, reduced, stuff like that. But I always get, because it's done in natural logs, isn't it? And I always get confused. So while I'm muttering away here, A-level syllabus, we are doing that one, aren't we? Please let this be the one. While we're looking at this, while I'm pretending I know what I'm doing, I'm trying to look up the syllabus because I just can't remember the Nernst. Is it log? Is it plus? Oh, who knows? All right. Oh, that's not good. Oh, is it on here? Let's have a look. Oh, God, I'm recording this lesson as well. I shouldn't say I don't remember it, should I? Right, here we go. It's near the bottom. Oh, wrong one. My computer's really slow today. All right. Do you know? All right. You know what it is. Okay. Thanks, dear. God, you're very nice to me today. I don't know why. Right. Let me get my thing back up. Okay. There it is. All right, dear. Tell me what it is. It's E electrode what? Plus. All right. Don't shout at me. I knew it was 0. I knew this number because this is changing natural logs, isn't it? Over Z's. That's the number of electrons. Log. What is it? Oxidized over reduced. I'll take your word for it. Oxidized over reduced. Okay, so there's the Nernst equation. And the Nernst equation doesn't tell you the cell potential, though. It tells you the new electrode potential. And students get this mixed up all the time. The new electrode potential. Okay, it doesn't tell you the cell potential. So here it is, and the oxidized form. So let's pretend we want to find out E electrodes if I increase the concentration. So let's go for 2 moles per decimeter cubed. Okay, is equal to E electrode, which is 0.36. This is the standard number. Okay, plus 0.059 divided by Z. Z is the number of electrons involved in the oxidation or the reduction. So that's over 2 log the oxidized concentration. Right, the oxidized concentration is this one because this is the oxidized state and this is the reduced state. So the oxidized concentration is 2 divided by the reduced concentration. Now, this is a piece of metal, isn't it? So we just ignore that and we just call it 1. All right. So there we are. All right. And now, are you understanding this? Am I making sense, by the way, while I'm gibbering on like this? I hope I am. All right. So 0.059 divided by 2 equals that times log 2 is equal to that. It's not a very big number, but now I'm going to add it to 0.36. And I get, oh, you know what? I don't get much difference. I get 0.369. Okay, which isn't much difference, is it? But can you see the electrode potential has gone up? Electrode has gone up. All right. I sometimes get confused on which one is the reduced. No, but that's not a problem, darling. Let me show you how the difference is. Okay, let's pick a system, the zinc system. Oh, and I put copper in there. I don't know where the copper came from. All right, there's the zinc system. All right, Ndibble, let's go through it nice and slowly. What's the oxidation of zinc here? Oxidation number of zinc there. Exactly. Plus 2. What's the oxidation number of zinc there? Exactly. Which one is the oxidized form of the zinc? The plus 2 or the 0? Debo, I'm waiting. Which one is the oxidized form of the zinc? Exactly. What's the question mark for? It's that one. Yeah, that's the oxidized form, isn't it? Simple as that. If you get confused with the oxidized reduced species, all you have to do is the one with the highest oxidation number is the oxidized. That's it. Simple as that. Yeah, well, yeah, in oxidation numbers, yes. That's as simple as that. That's all it is. All right, now I want you both, or how many have we got? We've only got two people here. And Moch is, that's disappointing. She's run off somewhere. All right. Ndibbo, are you a boarder, dear? Are you a boarder? Is Mochi around? She was the one that wanted this. Oh, she's not a boarder. Why do I always think she's a boarder? All right. Anyway, let's continue then. Now, I honestly thought she was. All right. Now, both of you have a look at the. Oh, she used to be. Okay. Have a look at the Nernst equation here. Okay. Now, ladies and gentlemen, or ladies, I should say. All right. If we have standard conditions, all right, what is the concentration of the oxidized form of this equation? What's the what number goes in here for yeah, exactly 1. Now, this is the clever thing. If 1 goes in here, yeah, well, this is going to be 1 as well because it's not in solution. It becomes 1 over 1, yes? And then we get the oxidation, sorry, and then we get 1 there. 1 over 1 is 1. And what's the log of 1? Anyone want to tell me what the log of 1 is? Oh, it's not 10, Debbie. What? It's 0. Okay, that was close. So, if this part is 0, this part of the expression disappears and the electrode potential becomes the standard potential. Does that make sense? If the concentration, and that's why we use the Nernst equation, because it goes back to the perfect situation under standard conditions and it doesn't under non-standard conditions. Does this make sense? Are we all happy with this? All right. Are we good? Excellent. Now I'm going to do a quick example there. I didn't want to talk about this too much, and I'll stop very soon because this is not what you came for. All right, I'm going to do a cell now between here. We're going to do zinc. Okay, this is zinc. All right, and then we're going to put a voltmeter there. And then, oh, that's not pretty ugly, isn't it? And then this is whatever it is. This is going to be copper. Okay, so this is zinc 2 plus, and this is zinc, and this is copper, and this is copper 2 plus. We need our salt bridge, don't forget. Okay, now under standard conditions. Oh, how do you spell conditions? Something like that. Under standard conditions, what is a cell? Okay, well, let's have a look at our individual E electrodes. E electrodes, standard for the copper system, is equal to plus 0.36 volts. And E electrode for the zinc system is minus, what is it? God, I've forgotten it. 0.74, I think. Is that right? Anyone? I think that's right. Okay. So these are the electrode potentials. Okay. So what's the E cell then? Well, E cell is this, isn't it? It's the more positive one. Okay. The E standard of the more positive minus E standard of the more negative. Okay, so what does that give us? The more positive is 0.34 minus 0.74. Okay, and therefore we get 0.36 plus 0.74, which is equal to 1. That's horrible. 1.1. Oh, wrong one. 1.1 volt. Does that make any sense at all? 1.1 volt. Are we good? Okay, cool. So you understand this? Yes? Okay, are we all good? All three of us, are we good? Right, so we've done that one. Okay, lovely. And so now, what is the new E cell potential if the concentration of copper is equal to 2 moles per decimeter cubed? Okay, what's the concentration now? Now watch. This is what everyone gets wrong. They think they can work this out just using the Nernst equation. And a student will do this. E is equal to E standard of the electrode plus 0.059 over Z into log oxidized over reduced. Okay. And they think, and this is what I'm banging on about, they think this gives the new cell potential, but it doesn't. It doesn't give the new cell potential. It gives the new what? Exactly, Tapio. You're good at this. It gives the new electrode potential. Okay, so what we've got to do is we've got to use this equation for copper, and as we've done already, we get that plus whatever this is 0.059 over 2 times log of 2, and we get 0.369, don't we? And then after we found the new electrode potential, and then we have to put it into this equation, the new cell potential. And therefore it is now, it used to be this minus 0.74, but now it's that minus that. So believe it or not, and this is going to go up a little bit, isn't it? It's going to be 1.19, I think. Is that right? 1. Something like, no, that's not right, is it? Is that right? No, I don't think it's right. I should do this. It used to be 1.1, but now it's going to be 0.1 there, 9 volts. So does that make sense? Are we good? Are we good? Now, I'm going to. So I hope you will understand that. And so the Nernst equation doesn't tell you. Yes, dear. Debbie, well, what is it? Oh, you're coming through loud and clear.
Sorry. So my question is: so when you see how when you reduce copper to ions, you get copper, meaning that the reduced species is a metal. So in the Nernst equation, you just take that as 1 or as 0.
Yeah, no. Oh, what the hell's going on? You've got a ghost in the room. Now, listen, dear. You can't take it as 0 because then you'd get infinity, wouldn't you?
Yeah.
So you got to take it as 1. Make sense?
So it's just not there.
What do you mean? What do you mean?
Like, did you say I can't take it as 1? Is that what you said?
Yeah, you do take it as 1, or you kind of ignore it if it's a metal, but it's taken as 1. Why do we have this here?
Okay.
Do you know?
Why do we have it?
When would this be kind of used?
Like Fe2 plus.
Exactly. Oh, that's wrong, isn't that? It's Fe3 plus an electron gives Fe2 plus. We do that. Now, Ndibo, which one would go on top, the Fe3 plus or the Fe2 plus? Well done. So the concentration of this would go on the top. Concentration of this would go on the bottom. It's as simple as that, dear. Simple as that. All right, now I was going to visualize this if you remember. Okay, so let's visualize this. Now, this is how I do it. I don't know about you guys, but I like visualizing things. Now you haven't got time in the exam for this, but it's a good way of doing it. Okay, so there we have the hydrogen system. Okay, and what's this? We call this zero. Copper is up here. Copper 2 plus copper, and this has a number 0.36. Zinc, or let's do blue. Zinc is down here. This is the zinc system, and this is minus 0.74. Okay, so if I did a copper with hydrogen, I'd get a cell potential of plus 36. If I did a hydrogen with zinc, I get a cell potential of minus 0.74. But if I did a copper and zinc, I get a cell potential of 1.1. It's just the difference, yes? And now, and this is copper 1 mole per decimeter cubed. And now if I did 2 moles per decimeter cubed, the electrode potential of the copper increases. So this goes to 0.369. And therefore, now the difference between this new copper system and the zinc is greater, isn't it? It's 1.019 volts. Does that make sense? Does that visualization make sense? Maybe it doesn't. We'll never know. This is how I do it. Now, obviously, you don't have time to do this in the exam, but for your revision or on a boring Saturday morning or something, you can just draw it out like this so you understand what's going on. This is how I always do it. Ndibo, do you understand that way of visualizing it? Ndibo, are you there, dear? Mohi, you're still not there. Oh, darling. All right. So listen, if I hook up the copper system to the hydrogen system, what electrode potential will I get? I'll get an electrode potential of 0.36 volts. Yeah. If I hook up the hydrogen system with the zinc system, I'll get an electrode potential of 0.74 volts. But if I hook up the copper and the zinc, I just add these two numbers and I'll get an electrode potential of 1.1 volts. But if I do a new copper, my non-standard copper, I'll get a bigger voltage. Yes? So, listen very carefully. Does that make sense now, Ndibble? If it doesn't, forget about it. Well, you'll have to come to school or something and ask me at school. But do you get it now? Kind of. Oh, I don't know. I don't know if I believe that one. All right. Now, so, do you get me when I say the Nernst equation tells you the new electrode potential, all right, but it doesn't tell you the new cell potential. You've still got to use the other equation. You've still got to find the difference between the two to get the cell potential. The Nernst equation just tells you the new non-standard electrode potential. Is that good? Are we good there? If we're all good, I'm going to move on now. Okay, are you all good? Excellent. So I'm going to move on to transition metals if I can. Okay. Now, oh look at all this mess we've done. Look at this. We've done. I can't believe we've done all of this. Crying out loud! How did we get about all this? Right now, I'm going to try. Oops, daisy. I'm going to try and get rid of this. So, and then we're going to do. Go away. You're not going away. And then we're going to do transition metals. Okay, let me get rid of this rubbish. All right, now, has it helped so far? Have you learned anything? Are we good? Have you learned anything? Is any whoops? Well, thanks, Nibble. You're very sweet. But the annoying thing, you know what, dear, is go on then, Debbie. Will say something. Put the mic.
Um,
Oh, yeah. Clear your throat before you answer the microphone.
sorry.
You know what? I'm being me because that's the sort of thing I do as well. Oh, it's horrible. We're horrible. Go on then. What is it, dear?
Before we start transition metals, I have a small question. It's about transition metals, but
Oh,
it's like a small question.
go on then.
Okay, so You know how in
I
the
can hear your notes moving.
yeah, my question is in my notes.
Uh,
Okay. Oh yeah, yeah. You know the where the color complex color compound thing. You know that
yeah,
one.
yeah.
So my question is, um, why does why must an electron be promoted? Like you know how the electron they absorb energy so that an electron can move from a lower energy level to a
Yeah,
higher one.
yeah.
Why must they do that?
Why
What's the
must
reason?
it?
Why does it promote?
Well, it hasn't. It hasn't got any choice, dear. It's like
But
if you kick a stone, yeah, has it got a choice not to move?
okay, I
No, but honestly, you
guess.
know you're overthinking
And
this, dear. Anyway, let me get on with transition metals for about 20 minutes or so. Okay.
okay,
All right. So let's go. Right now, I'm going to start nice and slow. Okay, which is the best place to go. Right now, I'm going to do this. I'm going to have some copper sulfates solution. And then to the copper sulfate solution, I'm going to add ammonia. Ooh, look at that. And then I'm going to get copper hydroxide because that's a precipitate. And then I'm going to add more ammonia. And then I'm going to get some weird stuff. I'm going to get copper. I can't remember what I'm going to get. I'm going to get 4 of those guys and 2 of those guys. And I'm going to get that. Okay. Now we're going to explain this transition from one to the other. And you may have done this in class, but it's actually quite confusing. So let's draw it out first of all. This is how I like to do it. I'm going to draw it, and in my first beaker here, all I've got is very simply, it's just all this is copper sulfate solution. That's all it is. All right, I'm going to add, what am I going to add? Ammonia. And now, crazy but true, I get a blue precipitate at the bottom. There it is. And this is copper hydroxide. And this is a blue precipitate. This first one, by the way, is a blue solution. And then I'm going to add more ammonia. This is ammonia. And now I'm going to add excess ammonia. Excess. And I'm going to get a beautiful, I really think it's beautiful, a lovely dark blue solution again. So we're all familiar with this, aren't we? This is a dark blue solution. Are we happy with this so far? Very simple, couple of reactions. Are we good with that? Are we okay with that? We're adding, this is a Form 5 thing, so we're all good with that. You know what, Nibble? You've got to start from somewhere where we all understand, and we all understand that. We start off with copper sulfate, I add sodium hydroxide, I get a blue precipitate, and then I add more ammonia and I get a deep blue solution. There you go. Now, well, what's going on? Okay, so now we get into the terms of weird stuff. Copper, there you go, copper ion is positive, and a sulfate ion is negative. Now, water molecules, as you all know, look like this H2O, but they have something very special about them. The oxygen is more electronegative and the hydrogen is more electropositive, so they have a dipole. All right. Now, we represent water molecules as V shapes. Okay. Now, around the copper, the negative side is going to come in, so it's going to be the oxygens going to be pointing in, but in the sulfate ion, it's going to be the other way around. The hydrogens are going to go in because of the relative charges of this, the water molecules, and the relative charges in the ions. All right. Now, crazy but true, we're not interested in the sulfate ion in this one because it doesn't do anything. We're interested in the copper ion only. Okay. So in copper sulfate solution, let's get a nice color. In copper sulfate solution, okay, we have these lovely copper ions, and there it is. Okay, and it's Cu2+. Now it's surrounded by what we call a ligand field. Okay, there and there. This is a pretty ugly one, I must admit. There and there and there. Okay, oh, that's a very ugly one, isn't it? Whoops. So we're going to get rid of this, and I'm going to put my line there. Okay, and we have water molecules there. It's always the oxygen of the water molecule because it's the oxygen that has the lone pair. Okay, now there's my lone pair, datively bonding to the central metal ion. And we can put arrows on to show it's datively bonded, like that. Now, you can't be lazy. We've got to put my hydrogens on, so I'm going to put my hydrogens in this darker purple. So this is water, 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 and this is water. Okay, and now, so we've got 6 ligands, so let's have a look at this. What's the formula of this guy? Well, it's a copper, Cu. It's got 6 waters around it, so we say H2O 6 times. And the oxidation number is +2, so we do that. So this thing is known as a complex. To give it the proper name, it's a transition metal complex. Okay. Now it is receiving 6 lone pairs. Okay. It forms 6 dative bonds to 6 ligands. Okay. Now each ligand donates 2 electrons. Okay, and if you only donate 2 electrons, that means these guys, each of them form 1 dative bond each. Okay, now, are you with me? Everyone's with me so far? I don't want to go on for too long on this because I think you'll get bored. All right, so each ligand forms 1 bond. Now, believe it or not, it's got 1 tooth. Yes, a water molecule can only donates 1 lone pair only. So crazy but true, we say it has 1 tooth. It only bites with 1 tooth. Does anyone know what I'm getting at? Anyone know what I'm getting at with this 1 tooth rubbish? If you don't know, say no, I don't know. IDK. What am I saying? Yeah, dentates, exactly. Okay, so a water molecule is a dentate, because that's tooth, and it's only got 1 tooth, so a water molecule is a monodentate ligand. Okay, and that's where we get the term from. It's only got 1 tooth, so it's a monodentate ligand. All right, now, since it receives 6 dative bonds, we say the coordination number is 6 because it makes 6 dative bonds. It doesn't have to have 6 ligands to be coordinate 6. All it means is it receives 6 lone pairs. Okay, that's why the coordination number is 6. And these water molecules are a ligand. Now let's define ligand. A ligand. What must the ligand have? Well, first of all, it must have a lone pair. Okay, and the lone pair forms a dative bond to a central metal ion. That's what a ligand is. Okay, now, beautiful as it is. Okay, this is my thing here. Now, what I'm going to do is I'm going to do this and see if this works. Whoopsie daisy. Okay, see if this works. I'm going to copy this thing. See if it's going to work. Oh, there you go, copy. And then I'm going to move this up. I'm going to paste it there. Oh, wonderful. It's worked. All right. Now, there's my H2O. So the coordination number is for the metal, not the ligand. It's how many lone pairs it receives in Dibble. Okay. So how many lone pairs does the metal ion receive? it receives 6. No, but you're right. In a way, you're right. Okay? It's about the metal, not the ligand. Because if you can imagine, if you have this, and now you're taking me off the topic, but that's fine. That's why we're here. Okay? Imagine this ligand. This is a lovely ligand as well. Okay, this is diamino ethane, and there's a lone pair there, and there's a lone pair there. Now, if we have copper here, okay, and these are my coordination sites, this thing, the thing I've just drawn, can form like this: N N N N N N. Okay, and it forms like this. Okay, so this guy here, how many ligands are attached to the copper? Exactly, there are 3 ligands. What's the coordination number of the copper? Exactly, 6 is coordinate. Yeah, that's exactly right. What are these ligands called? Not the name of them, in terms of how many teeth have they got. Exactly. Exactly. These are bidentate ligands. All right. So well done. Now let's get back to our thing because I want to get off in about 5 minutes' time. Eh? Now, to be honest with you, I don't know if you agree with this. I know you're going to shout at me, I'm sure, but I don't like lessons that go over an hour. Okay, that sucks for everyone. So maybe we can do one tomorrow. I don't know. Is that okay? Can we continue this because there's quite a lot to do, and I don't think we'll finish this. Yeah, I know. I'm asking a lot from you guys, but we'll think of a different time, maybe a little bit earlier on a Friday. Okay, but we'll see. All right, we'll see. Now, this is my copper iron. This is called Cu2 plus aqueous. Now, when I add ammonia, if I add ammonia, and there's ammonia, okay. Now you're thinking, well, you're adding ammonia. Well, believe it or not, I'm not adding ammonia. What I'm doing is this. Ammonia, when you dissolve ammonia in water, this equilibrium is set up. You get the ammonium ion and the OH minus ion. Yeah. Now, what happens is this. All right. Along comes an OH minus, and let me draw this a bit better. Okay. There's my water molecule there. And then there's another water molecule here. And along comes my OH minus ion. So it's all about that guy. Let's make it nice and red. So here it comes. OH minus. This guy's OH minus. Okay. Now, this is what happens. Let me get a nice color. Oh, there you go. This color's nice. What happens is this. These electrons grab this proton, and these electrons go onto here. Okay, now it happens this one as well down here. Whoops, wrong color. Oh, why is it? Oh, did I change colors? I think I did. Yeah, who wants green? No one wants green. So this OH here, OH, does it again. There's the lone pair. And these electrons capture this proton, and these electrons go on to here. Okay, so what's the outcome of this rubbish? Let me show you. Let's move that over there. Let's paste again. Okay, now what happens is let's get rid of that. Let's get rid of that. Let's add the H and the H. Now the 2 protons have gone. This proton has gone, and this proton has gone, and it joins this OH to form water. Okay, but these are now OH minus ions, aren't they? Because they took the bonding pair. Okay, now would you call this ligand exchange? Is this a ligand exchange reaction? Anyone want to guess? Is that a ligand exchange? Yeah, exactly. I don't think it is either. And more importantly, no, that's fine. It did a ligand exchange. Did an OH go on and a water come off? No, it didn't. How would you best describe this reaction? If you had to call it anything, what would you call it? Anyone? It's actually not an oxidation, believe it or not. It's a good guess though, but it's not an oxidation. It's not an elimination either. You do know when I tell you, you'll go, oh. Well, I don't know if you say it like that, but you'll go, ooh. So, what's it called? No, well done, everyone. No. What's being transferred from the complex to the water? Yes, so therefore you know the reaction. Tell people you're right. And therefore it is a what? Exactly. It's an acid base reaction. This is an acid base reaction. This, the water, this bit here is acting as our acid part, and the OH minus is acting as a base. So it's actually not a ligand exchange, it's an acid base reaction. Now, this is the crazy thing. This guy, copper ions, okay, they have big interactions with water molecules and they dissolve, okay? But now, if I've got my copper ion and I hitch onto it two OH minus ions, it's now neutral. And because it's now neutral, it cannot form ion dipoles with water. Now, copper ions are soluble because they can form ion dipole interactions with the water. But this guy here is neutral and it's no longer an ion. So it can't form ion dipoles with water. And because of that, it precipitates out as a blue precipitate. And what's the blue precipitate we see? We see CuOH twice. We see copper hydroxide. Copper 2 hydroxide. And that's why copper 2 hydroxide forms. Oh, that's why it precipitates, I should say. But it's an acid base reaction with the OH minus ions from the ammonia. Ah, it's clever, isn't it? It's beautiful. Transition metals is beautiful. You guys hate it, but it's absolutely beautiful. It really is. Now, guys, it's 9 o'clock or very close to 9. So, and I don't want to rush anymore. So I'll finish it here. Okay, let me finish the video so we know we've stopped.